In the introduction, and thanks to the organizers for inviting me. So, as Sebastian said, I will talk on two subfactor theory. So basically, as I told in the abstract, Vaughan Jones introduced subfactor theory. So this is basically how one sub-algebra is embedded inside another algebra. That algebra is simple, basically. So that's called two-one factor. So there is only two algebras involved. One factor, how it is sitting inside another factor. But Oknaniu and Vaughan Jones has later thought that it is equally important to consider many subfactors. So what are the relative position? They ask what are the relative position of multiple subfactors. But unfortunately, not much has been done because theory becomes quite complicated. So I shall attempt to explain some of my small contributions to this project following Popa's work, Jones, Grossman, Izumi, and Oknaniu's work. So let me start from the beginning. What is a subfactor? So I will explain those things as there are many experts. Sorry for them, so because they already know those things. But let me very briefly introduce those. So a subfactor means some inclusion, like a group and a subgroup. Here, a factor inside another factor. And the most important invariant is called planar algebra by Vaughan Jones. And this is complete invariant for large class of subfactors. So as I said, there are multiple subfactors involved, then what will happen? So the most easiest example is this intermediate. So we have given this n subset m, but suppose there is another intermediate subfactor, like you have a group H and G, but there is an intermediate subgroup like that. So, but this is the simplest example. Then, so as I said, planar algebra is the most important invariant. So, in following Landau and Veena Bhattacharya's work, I have done an alternative approach where we have found that planar algebra of n subset P in terms of the planar algebra of n subset M. Probably in our approach, you can find a lot of detailed versions of the proof. So basically, what I'm saying that that in invariant of n subset P, just give me 1 second, just. Sorry. So the invariant of n subset P in terms of n subset M that we have done. So this is in the IJM paper in the irreducible case, and we have done in the non-irreducible case. I will explain those terms. So this is very recently with Shruti Murali we have done. So basically this is well understood. If there is one factor involved, this is well understood. But what will happen if you have multiple subfactors? So you have a subfactor n subset M, but suppose now you have two subfactors P and Q. As I said, P is understood, but what will happen for P subset Q if there are two subfactors P and Q? So actually, you can think in this way. Suppose we have two subfactors M, P subset M and Q subset M. So this is one subfactor, this is another subfactor. Can you build a invariant for this? Can you build a theory on this, like single subfactor theory of Vaughan Jones? This is called two subfactor theory. But main problem is that it is this one. The problem this, if you have two subfactor P subset N and Q subset M, this is extremely difficult. So for simplicity, we have assumed that there is a common subfactor N, and this is called a quadruple. Quadruple of one factor. So this throughout my talk, there is a common subfactor N, otherwise not much known. So, so there are few invariants for this two subfactor theory. So first one is angle between two subfactors. So two intermediate subfactors. This is in a joint work with Sayon Das, Jongwe, and Junxian. So where we have introduced a new notion of angle. So like in plane geometry, we know that there are angle between two lines. Similarly, here, if you have a two subfactors P subset M and Q subset M, and there is a intermediate, there is a common subfactor n, then we can introduce the angle between these two. So this is in the joint work with Liu and others. In that, it was successfully done because in that in this is in the transactions of AMS in I think 18. So in this paper, what the novel thing was that we could answer an open question asked by Roberto Longo regarding some cardinality of intermediate subfactors. So I will come to that if I have time at the end of the talk. I will talk on angle, but in this talk I don't want to focus on angle. So, but very nice thing probably was that we have found some connection between Kissing number in geometry and rigidity of angle. So that angle, like Jones index, was very rigid, as you can see in my talk. Similarly, this angle, we have found that angle also very rigid, and there is a relationship between Kissing number and this thing. And we believe that, like Jones index, that angle might be a nice invariant for two subfactor theory, and lot of future research should be done on this. We don't know much on, for example, possible values of that angle, and we need more applications of angle. So this is one nice research direction. But there are other things of two subfactor theory. There are other invariants. So there are two other. One is called Pimsner-Popa probabilistic constant. This is from old work of Popa. So this is one invariant for two subfactor. Another one is Constormer relative entropy. So my talk will be focused on these two invariants. Now let me do very preliminary very quickly. Most of you know already. So our playground is B of H. So this is H is a separable Hilbert space, and B of H is a bounded linear operator on Hilbert space. So T is a bounded operator from H to H. And what is a von Neumann algebra? This is nothing but some WOT closed subalgebra of B of H. So AM is a certain subalgebra of B of H. It is closed in some locally convex topology. That is called weak operator topology. And there are various equivalent definitions. I don't want to go to that, but let me mention the reference, those you are interested. So it is done by von Neumann in 1929, and later major part of this theory has been developed with his postdoc collaborator Murray. And this is in a series of paper called Rings of Operator in Annals of Math. So please, you can interrupt me at any time if you have any question. Don't hesitate, please. So this is a von Neumann algebra, and there is this famous double commutant theorem, which says that this is more algebraic. So a von Neumann algebra is nothing but a subalgebra of B of H such that M equals M double commutant. Double commutant means what? Double commutant means when taking one commutant and then another commutant. So what is commutant? So M is a subalgebra. M is a subalgebra of B of H, and commutant means all elements in B of H which commutes with M. And then it is AM equals M double prime. That is the definition of von Neumann algebra. You can take this double commutant theorem as the definition of von Neumann algebra. This is more algebraic, and the previous definition, what I said, was topological. So the beauty is that von Neumann proved that these two are equivalent. Now let us consider a pair of inclusions of such von Neumann algebra n subset M. And there is like the classical conditional expectation, like we have a probability space and another sub sigma algebra. Then we have a notion of conditional expectation. Similarly, if we have a sub algebra, we have a notion of conditional expectation, which generalize that classical conditional expectation. So it is a norm one projection, and this is a bilinear map. So this is modeled by that conditional expectation from probability theory. Now, when is a factor? So building blocks of von Neumann algebras are called factors, in the sense that a von Neumann algebra can be written as a direct sum of certain simple algebra called factors. So what is a factor? Means its center, which is defined as M intersect M prime, center is trivial. Or in other words, it has no closed ideal. Whichever topology you take, norm, all will be equivalent, you can prove in sigma, in this weak operator topology. So there are no ideal. For example, one example is MNC, n by n matrix. So this is clearly trivial. Center is trivial. So it is a simple algebra. So it is called a factor if this happens. According to the behavior of projections, factors are classified in various type 1, type 2, and type 3. I don't want to go to the details. Our main focus will be only focusing on type 2 one factor. So it is basically infinite dimensional analogs of matrix algebra. So what is that? So basically it is, like what is special about matrix algebra? That it has a trace, right? Just take the sum of the diagonals. It has a trace. Similarly, 2-1 factor is nothing. It is an infinite dimensional factor and has a trace. Trace means there's some positive map from M to C such that it satisfies this property, like the matrix trace. Trace of xy equals TR of yx, like that. So there is a trace. That's it. The trace means a linear functional which behaves like the matrix trace. But main thing is that it is infinite dimensional. So these are called type 1 factor. Now there is a Gelfand-Neumann-Segal construction, GNS construction. As soon as M, now from in my talk, everything will be 2-1 factor. All Von Neumann algebra, all factors will be 2-1 factor. So on M we have a trace, right? So using that trace we can define an inner product. And using that inner product, M becomes, and its completion of M becomes a Hilbert space, which we denote by L2M. This is again in the analogy of LP space, basically. Because any commutative Von Neumann algebra looks like L infinity X mu. And then the measure defines a trace. And then if you do the GNS, you can get L2 X mu. See, so in that analogy, if you keep in mind, then you will understand why it is called L2M. So this is the GNS construction. Now, M can be thought of as a sub-algebra of B of L2M. L2M, remember, is a Hilbert space. By left multiplication, it sits inside B of L2M. Now, let us have some examples. So, suppose, sorry, when can I finish? Actually, I start later. So, what is the time?
According to have 1 hour and more. Actually, we can end at 12, hour 12. So, in an hour, so you have plenty of time.
Okay, fine. Yeah. So thank you. So basically I will say some examples. So suppose you have a countable discrete group, and as you know, there is a left regular representation which is basically mapped from G to unitary elements of L to G. L to G means its basis are delta S, like the Kronecker deltas, and S are elements of G. So what lambda does, lambda is a homomorphism from G to U, L to G. That means lambda of G acting on delta S, nothing but delta G dot S, that group operation. More precisely, it is this one. So this is called left regular representation, and everything happening in B of L to G, right? So it has a weak operator topology. So take lambda of G and then take the weak operator closer. So you get a Von Neumann algebra L of G. This is called group Von Neumann algebra. Nothing special about left regular representation. You can take right group Von Neumann algebra also, and there is a really nice relation that this is a prime of other. So yeah, so this is called a group Von Neumann algebra. So from a group you can define a Von Neumann algebra, and as you know, there is a famous open problem called free group factor. So yet it is not known whether this is isomorphic to as a Von Neumann algebra. These two are isomorphic or not for M not equals N. So, this is not a lot of structures are there actually in group Von Neumann algebra, not well understood in some sense. Okay, but on the other way, this is the simplest example of non-trivial Von Neumann algebra. Now, our question is when LG is a factor, because we are, and more generally when it is a 2-1 factor. So it can be shown that it will be a factor. If it is a factor, it will automatically a type 2-1 factor. So fact is that LG is a factor, type 2-1 factor, if and only if G is so-called ICC group. That means its conjugacy class of non-trivial element is infinite. So this is called ICC group, infinite conjugacy class group. And examples are plenty. For example, infinite permutation group and free group with n generators. And also, if you have a ICC group and any finite index subgroup, if you take, that finite index subgroup will be also ICC. So from a ICC group, you can form many ICC groups. So, and given any ICC group, L of G will be a type 2-1 factor. So we have an example of type 2-1 factor. And it can be given a natural trace because as one factor has a unique trace. So, and this is the unique trace, the identity component of the representation of element of X. So how to obtain other factors? So suppose you have a type 1 factor M, can you produce another new kind of type 1 factor? Yes, it can be done. So here even you consider a finite group G, and then suppose G acts on M. So if you have a nice action, then Mg, this is the fixed point. Fixed point means set of all element in M which which fixes by action. So this is Mg, fixed point algebra. And for nice action, so-called outer action, like ergodic theoretic action called free action, if you have these nicer actions, then this will be also a 2-1 factor. And also one can, there is certain notion called cross product construction. So this will be also a type 1 factor. I won't go to the details of cross product construction. So it is like some twisted tensor product kind of thing. You can, I mean, M tensor B of L to G, and then some kind of twist you can think. So anyway, but later via Jones index theory, you will understand this better in my talk. So this is called cross product construction. So out of 2-1 factor M, you can produce another 2-1 factor. And therefore, what we got, so basically, yeah. Okay, so what we got, an inclusion of 2-1 factor, Mg subset M. Or more generally, if you have a subgroup and a group, we can have this inclusion, Mg subset Mh. And also we have M subset M cross G. So this is an inclusion of 2-1 factor. And also more generally for subgroup, and this. And nice thing is that this encodes all the subgroup theory by work of Jones, Cohn, and Oknaniu. This whole subgroup theory can be thought of as is subsumed by this subfactor theory, by this subgroup subfactor. These are called subfactor. Whenever we have an inclusion of 2-1 factor, unital inclusion, these are called subfactor. So other example, for if you have a ICC group and a subgroup, LH subset LG. So these are all examples of subfactor. Now this really groundbreaking work started from Vaughan Jones. So the simple, I mean, this is very nice and but simple ideas. Like if you have a group and a subgroup, we have a notion of index. So in his invention, his paper, what he has done basically, this paper name I have not written. This is called Index for Subfactor. This is in 1983 in inventionist math. So what he has done, given this subfactor n subset M, he has introduced or discovered a notion of index. And the beautiful thing is that this generalizes the subgroup index. So if you have this group subgroup, we have this index. We can get back the subgroup index. So, and more generally, LG, not more generally, and also LG index LH will be also G index H. And if you take the fixed point, NH index NG, because that is also a subfactor, it will be the G. So this can be really thought of as a index, as a generalization of subgroup index. And the way it has been defined, it is basically the GNS construction L2M can be thought of as NN bimodule. And Mare Vonneman has done some that there is something called dimension function or coupling constant. So using that dimension, it is the dimension of L2M as a left N module. I cannot define all these things, but later you will see that we have an alternative, various definitions, alternative definitions. So, but what is the groundbreaking idea is that in that same paper, he answered that what are the possible values of index. So basically it says that there is a strange rigidity. So after 4, it takes all the half line, all values between 4 to infinity, it takes all the possible values. But before 4, it takes only discrete values, 4 cos square pi by n. So first value is 1. And then surprising thing is that next value is 2. And in between 1 and 2, there are no values. So it continues like that. 4 cos square pi by n. And also this is the fact that if index is 1, if and only if n equals m. So these are the things. So after 4, then after 2, it will be related with this golden ratio. And the possible values will go like this, and the limit will be 4. So basically you can see this, the limit will be 4. So it will be 4 cos square pi by n. This is famously called Jones index rigidity. So these are the possible values of index. And it's already done. So yeah, so let us continue with this subfactor theory. So so what is there? So we have this inclusion n subset m, and from m we have a Hilbert space L to m GNS construction. So similarly, because you have a trace on m, if you restrict that trace on n, you will get another trace. But this is the unique trace, because 2-1 factor has a unique trace, one can easily prove. So so that using that trace also from n, we can define another Hilbert space L to n that do the GNS construction. So we have a inclusion of Hilbert space L to n subset L to n, and that was the key point. So we have an inclusion of 2-1 factor. Now we have an inclusion of Hilbert space. Now you can do the geometry. So as soon as you have a this notion of you have a subspace, and this is a clearly closed subspace. So we have a projection, Hilbert space projection. These are called E sub n. These are called Jones projection. And this was the key thing, one of the key thing in Jones index rigidity. And a nice thing is that this Jones projection induces that conditional expectation. As I told in the first few slides, that given an inclusion of Von Neumann algebra, there is a notion of conditional expectation, n subset m. There is a notion of conditional expectation, and this conditional expectation is intimately related with this Jones projection. Here omega is the cyclic vector of GNS construction. So you can think as that is the Jones projection, basically conditional expectation in the Hilbert space level, in the subfactor level. This is in the Hilbert space level. So this Jones projection is related with the conditional expectation. Basically, the restriction of the Jones projection on the factor m. Okay, I won't say much on this. But this I should say that conditional expectation, which is a map from m to m onto n, this is trace preserving. By that I mean trace is a map. Remember, trace is a map from m to c. So if you take trace of en of x, where x is in m, you will get back that trace of x. So it is trace preserving, like that conditional expectation. If you remember the conditional expectation in probability theory, this is exactly the trace preserving condition. So this is nice. Now, interesting thing happens when a subfactor is finite index. So we'll only focus when a subfactor n subset m, that index is finite. Otherwise, not much is known actually. So this is done by a celebrated paper by Pimsner and Poppa in 1986, where they have shown that given a finite index subfactor, there is a certain notion of basis. And so these are certain finitely many elements inside M, such that any element of M can be written as in terms of that conditional expectation. This you can think as n-valued inner product. So this is really like the basis. So just remember that these are elements of M. So this will generate whole M, this finitely many elements. So this is a finitely generated module, that M. So for the subfactor R cross H, always remember this analogy with the subgroup. R cross H and R cross G, the coset representatives is the basis. And then there is a notion called, which is very crucial in Jones index rigidity, I talked earlier. This is called Jones basic construction. So what this beauty is that given a subfactor n subset M, Jones produced another subfactor M subset M1. M subset M1. So this M1 also sits inside B of L to M. And nice thing is that this index, M1 index M, this is same as Jones index. So this M1 is called this procedure to obtaining M1, another 2-1 factor from the old subfactor N subset M, is called the basic construction. So for example, you can understand that if you have a fixed point subfactor Ng cross N, if you do the basic construction, you can get the cross product. So you can understand cross product as a basic construction of fixed point. So this is one example. And I have not really defined Jones index, but using basis, you can immediately define the Jones index. But I mean, basically, yeah, this is alternative formulation, because remember that PIMSA and Popa proved that if the index is finite, there exists basis. So we can define Jones index like that, that given a subfactor, we say that it is finite index if there exists basis. We can say that. And so we have this subset of M, then it is a basis if and only if this sum holds. And then we can define Jones index like this summation lambda I, lambda I star. One caveat is that if you have another basis, so mu j, still that sum will be constant. So these are same. The summation mu j star will be same as summation lambda I, lambda I star. And the same, this quantity is a scalar. That is one of the thing in PIMSA basis. So, and this is called the Jones index. This you can define as Jones index. And then the Jones basic construction, one can iterate it. That has been shown another paper of PIMSA and Popa in transaction, that given a 2-1 factor n subset of M, we can obtain M1. Right. Now consider M subset M1. Do the basic construction. So you obtain M2. Like that, you obtain a chain of subfactor Mk, and each one is periodic. So the index will be same. This is called Jones basic construction, and you can obtain a many Jones projections. So n subset M1, E1 is the Jones projection for M1. Now M subset M1 and M2 for that E2 is the Jones projection. So you obtain a chain of Jones projection Ek, and these are related with temporally leaf algebra, and that was the key ingredient in Jones polynomial, planar algebra, all the aspects of subfactor. These are the key aspects, the Jones projection. Okay, now another thing. So as soon as we have a subfactor, we need an invariant. So this invariant is called planar algebra, and the skeleton of planar algebras are relative commutants. So what are the relative commutants? Relative commutants are basically, as I said, n prime intersect M. If what is that? It is a set of all elements in M such that this commutes for all elements in N. So elements of M which commutes with M. Similarly, n prime intersect mk minus 1. Mk minus 1, remember, this is the multiple basic construction, iterated basic construction. So it is the element of mk minus 1 which commutes with n. So these are called nth relative commutant. And it can be shown that these all are finite dimensional, that n prime intersect mk are finite dimensional. So this, we have another inclusion of finite dimensional sister algebra. This is the finite dimensional sister algebra when we take sum of matrix algebra, semi-simple. So this is also semi-simple. So we have easier thing. So we want to approximate the difficult thing, which is infinite dimensional subfactor, in terms of these easier blocks of finite dimensional things. So this is the key notion of planar algebra or standard invariant by Popa. Okay, these are called relative commutant. And a subfactor is called irreducible if this n prime intersect M is scalar. So there n subset M is called irreducible if n prime intersect M is just trivial. This is called irreducible. Examples are these: subgroup subfactor n cross H and n cross G for nice action. Okay. Now I talk about PIMSA-Popa index. This is a nice picture of Voiculescu and PIMSA and Popa. So in PIMSA and Popa, what had described certain notion of probabilistic index for an input. There is another way to look at index. So given an inclusion of Von Neumann algebra, so B2 subset B1, one can describe certain probabilistic index lambda B1 comma B2, which is nothing but supremum of all scalars such that EB2x greater than equals lambda x. So it is called probabilistic because one of the reasons is that it involves that conditional expectation. This supremum, actually this is not just supremum, this is the maximum basically. So this is called, this is certain invariant for this kind of inclusion, B2 subset B1. It's called PIMSA-Popa index. Why this is called again index? Because this has been done by Pimsner and Popa, that if you have a subfactor, these two notions, lambda m comma n subset m, already we have a notion of index. And now we have a notion of probabilistic index in terms of this conditional expectation from B1 on to B2. So this is how flat elements of X in terms of this conditional expectation. This says this is the measurement of that. I cannot motivate this now, but probably later you can see in the two subfactor theory how this will again come up. So this is also same as Jones index. So this is another way of looking this. And the main thing is that there is a projection inside M such that if you do the trace preserving conditional expectation, you will get back the Jones index. That was the key thing in defining that probabilistic index. Now, as I have told you that given a subfactor n subset M, you can go on and obtain a chain of subfactor M1, like that basic construction you can do. Now let us come back to our two subfactor theory, our research. So here we have a two subfactor M subset Q and M subset P and a common subfactor N. Now we can do the similarly we can do the basic construction of the quadruple. So basically for P subset M, if you do the Jones basic construction, if you do, you will get another 2-1 factor P1. For Q subset M, you will get another 2-1 factor Q1. So we obtain a dual quadruple P1, Q1, M1. So out of a 2-1 factor, two subfactor Q and P, we obtain another 2 subfactor P1 and Q, which lies inside M1. Remember, M1 is N subset M's basic construction. So this is called so basic construction of this quadruple is this quadruple. So this has a nice picture here. So we have already these two subfactor P and Q. We have done a basic construction, obtain P1. Basic construction of Q we have done and obtain Q1. And basic construction of N is M1. So from this quadruple we obtain that quadruple, and that will be important again as usual. So I don't want to do angle things now. So if I have time later, I will see. Let us skip this because I don't have them. So let me go back to the Pimsner-Popa probabilistic constant. So you can see that Pimsner-Popa's definition you can just modify, and that will exactly work for the 2-1 factor also, for two subfactor P and Q also. No need that P is subset of Q. The same definition, supremum. We can no longer write maximum, but the supremum of all T such that EQX greater than equal to TX. So here I have taken X positive element from P plus, and then we have expected to Q. So we have considered all such scalar and took the supremum. So this, we believe this lambda PQ is an important invariant like angle for this two subfactor theory. And nice thing is that one can easily prove that it lies in between 0 and 1. And this is another reason why it should be called probabilistic index actually. So, so this is in between 0 and 1. So this is an important invariant. And now next question, like this is, we can think of as the measurement of the relative position in between P and Q. So like we have the measurement for the subfactor N inside M, we have this measurement called index. Now we have another new measurement, lambda PQ. Jones has tried this question. Jones has done this question that what are the possible values of index? So natural question, what are the possible values of this lambda PQ? Now, this is what I have done in proceedings of AMS recently, that but under this irreducible condition. We don't know beyond that. So if you have a subfactor which is irreducible, then we can give an explicit formula of lambda PQ in terms of the Jones projection. See, here I should say, what to say here. Yeah, so what is this EP? So remember that N subset M we have, and then M1, the Jones projection, that the Jones projection is En, right? Similarly, for P subset M and for P1, EP, E sub P is the Jones projection. And this trace is everything happening in M1. So that is why I said that middle subfactor, this common subfactor N is very important. Otherwise, I don't know the proofs. So we have this condition, we have this two subfactor P and Q, but we have this extra assumption that there is a irreducible common subfactor. Then I can explicitly give a formula of lambda PQ, and this came from the one of the idea came from my our paper with Zhongwei and others, that there is this EP star EQ, that is the P operator in terms of the basis we have, and using that we have a notion of, we have a projection. Like in the n subset M, we have already some projection in M, and similarly here also we can have a projection, but for that we need something called downward basic construction. So I mean, because here that why we have a in Pimson and Popper's construction, why we have a projection E such that ENE is the Jones index inverse, because of downward basic construction. Similarly, here also we can have a downward basic construction, and then I don't want to go to the detail of these things. There are some manipulations I have done. What is downward? Just let me, I won't go to the detailed proof, but let me say the downward thing. So as I said, from n subset M, we went to M1 for the forward direction basic construction. Similarly, you can get in the downward direction, we can obtain another 2-1 factor n minus 1, such that this n minus 1 subset n, this basic construction will be n subset n. So this similar thing one can do for the quadruple also. So we can obtain a downward basic construction of a quadruple. And then we have obtained this P, using this P operator, we have found a projection, and using this projection and complete positivity of conditional expectation proves that result. So this is some kind of modification of Popper's ideas and our angle ideas, and something little bit work. So that follows that in the irreducible case we can give an explicit and very and probably useful formula of lambda PQ, and this generalizes that Popper's thing is that lambda is the generalization of Jones index. For if P and Q are same as N, then we get back their result. So and later you can see that this proposition has an application in entropy. So let me quickly say so for the pair of subfactor, nicest thing is the commuting square. So this is like independence of two random variable basically. So suppose we have a quadruple P and Q, we say when it is a commuting square, if this conditional expectation EQ and this conditional expectation EP, this commutes. So if this diagram commutes, and in terms of our angle, one can say that this angle will be pi by 2. So 90-degree angle is equivalent to that commuting square condition, and this is very important in subfactor theory, this commuting square. So in the commuting square case, as a corollary of my result, one can prove that lambda PQ will be Jones index inverse, lambda PQ. Similarly, lambda QP. By the way, lambda PQ in general not equals to lambda QP. Although the angle between PQ and angle between Q and P are same. So this lambda is actually when occurs, it's more general than this angle thing, because in angle we need the middle the common subfactor n. So we have P and Q, we have this common n, but to define lambda we don't need that n. So in the sense that it is more difficult to obtain the possible values of lambda. Now of course the angle also very difficult to know, but on the other hand you can think in this way that angle is also more calculable in some sense, in relatively more calculable than lambda. And we can explicitly for the group and the subgroup. So we have a 2-1 factor hyperfinite 2-1 factor R, and we have a subgroup H and K, RK, suppose RG. Then we can explicitly write the formulas of lambda PQ in terms of that formula I have given. So here is this, and nice thing is that this theorem again. So here is the thing, we have this quadruple. Now, and from this quadruple, we have a basic construction, right? M1, this is P1, this is M1, and this is Q1, and this is M. So we have this. A nice thing is that this, like we have seen that if we have n subset M subset M1, then M1 index M is same as M index N, this periodicity. Similar thing happens here also. That lambda, this can be easily shown by planar algebra basically, and using my formula. So this is lambda P1 Q1 will be same as lambda QP, and similarly lambda Q1 P1 also will be same as lambda P comma Q. use this pictorially, it beautifully it follows. Basically, one advantage of this planar algebra that of Jones actually, that lot of analytic things you can draw by pictures, and proofs will be more handy. Basically, it will be more easier. So this is the formula between this, and apply that formula of lambda I obtained here. This, then from that it will follow trace EPQ divided by trace EPQ. Okay, so this is all about Pimsner-Popper constant. Now I come to the Kohn-Stormer relative entropy. So this is in an old paper. What he has done, Alan Kohn and Stormer. So given a pair of finite dimensional von Neumann subalgebra of P and Q of a finite von Neumann algebra M, you can assume that 2-1 factor. We have a notion of relative entropy P given Q, and this is perfect generalization of conditional entropy, classical conditional entropy from information theory or ergodic theory, and this is the correct generalization of conditional entropy, because they could prove that Kolmogorov-Sinai type theorem. And using this relative entropy, Kohn and Stormer has defined entropy of an automorphism. So, but Pimsner and Popper, what they have observed that we don't need finite dimensionality. So, for example, if you have any 2-1 factor and any subalgebra, infinite dimensional also, P and Q, one can have a notion of relative entropy, HP given Q. So these are all generalization of conditional entropy from ergodic theory. This is, you can say that this is the starting point of non-commutative ergodic theory. This is in Acta Mathematica in around, I think, 70s, 1978 or 76, I forgot. So this is really we call it Kohn-Stormer relative entropy. We call this one that Kohn-Stormer relative entropy for P and Q infinite dimension. So so this is the nice picture of two subfactor theory. Here there are nothing common. You can still define this thing. And this definition is a little bit involved. So suppose this is motivated by conditional entropy, because there we have a entropy between two partitions. And here partitions are characteristic functions and which are projection, but they have, Kohn and Stormer have seen that we don't need projection, because sometimes finding projections are difficult. So positive element will do basically. So what they have taken, I mean, this is the modification by Pimsner and Popper. So given a type 2-1 factor or any general finite von Neumann algebra, tracial von Neumann algebra, and you have a two von Neumann subalgebras, P and Q, then we consider the set of all partitions of M. So positive element with sum is 1. And this ergodic theoretic, that eta actually, that concave function, that t going to minus t log t, if you take this and using functional calculus, one can define that relative entropy by fixing one partition, gamma. So this is the trace preserving conditional expectation and eta map, and we have used the trace. Trace is the trace of the 2-1 factor. And now what they have done, they have taken the supremum. That is the beauty of this non-commutative version. They have taken the supremum over all the partitions. So see, this is related this is more general than the classical, because this tau is related with the integration actually. As you can see, using this trace, we can do non-commutative integration theory. So instead of that integration, we have now trace. So this is called Kohn-Stormer entropy. And one can easily prove that this is positive and it is 0 if and only P subset. This is powerful. So it is 0 if and only P subset of Q. And nothing much is known about this entropy basically. But Pimsner and Popper, in again that groundbreaking paper where this basic construction, all these things he has developed, Pimsner, Popper, basically in the same paper, they have proved that this. So they consider this subfactor and consider this relative entropy M given N, and then found that this is surprisingly related with the Jones index. So and they characterize when this index, they proved that for irreducible subfactor, irreducible, remember, means n prime intersect M is scalar. They proved that age of M given N is nothing but logarithm of Jones index. And this is more generally, this holds for extremal subfactor. And this is the characterization. I don't want detailed description of extremality. So a subfactor is extremal if something happens on the trace, actually on the relative commutant. So this is equivalent to that age will be equal to logarithm of index. Again, this is for one subfactor, m and n and m. And more generally, they have proved this. This is the theorem that a subfactor is extremal if and only entropy is equal to logarithm of index. And this is a lot of work is needed. And more generally, they have proved, even forget about irreducibility, even for infinite index also they have proved. But let me focus on finite index. And if you have these atoms, take the atoms of n prime intersect m, that means minimal projection with sum is 1, then we can give a explicit formula of index of that constant of entropy. However, still the explicit computation is very difficult, and that paper was devoted to given explicit computations of entropy even for finite dimensions. So this is a very important paper. Now my question is how to calculate age p given q if you have a this pair of subfactors. And again, for simplicity, I assume n, otherwise nothing is known. But this seems to be extremely difficult. But the small result I found in this same paper where I talked about lambda pq, that is the one of the reasons that we have found the value of lambda. So for the irreducible subfactor, we can, and we have irreducible means n prime intersect mc, always remember, and also this finite index. Otherwise, also I don't know anything. If you have finite index, then age is equal to minus log lambda p. That is the perfect generalization of that Pimsner and Popper's earlier result. So age p given q is minus log lambda p comma q. And I won't go to the detail. There are a lot of technical lemmas are there. So and using that lambda's explicit formula, corollary is that I can give an explicit formula of h q given q in terms of Jones projection. So hopefully this is calculable, and recently we found some applications of this formula. Okay, so this is that this is only for irreducible and finite index. Yeah. And as I said that lambda p1 q1 is equal to lambda pq, I proved that p1 q1 is the basic construction of the quadruple. And using this earlier result, we can prove that for the basic construction of the quadruple p1 q1, this entropy is also invariant. H p1 q1 comma p1 is same as h p given q. Oh, sorry, this is h q1 given p1. Remember again, as usual, this is not true. HQ given P not equals to HP given Q. This is not commutative. And one applications which is like the Jones index rigidity, using that earlier work of mine in PAMS, I can prove that if you have this quadrilateral, that means if you have this M here, P and Q, N, such that P join Q is M and P meet Q intersection Q is N. In that case, these are same. HP given Q and HQ given P are same. If you assume that this index and that index is less than 4, this is by fundamental works by various mathematicians, that one can classify subfactors for small index subfactor. Remember, but after 4, that I mean, it's not easy to classify subfactor. Beyond 6, nothing is known basically. But following their work and our recent work on PAMS, my recent work, I can prove that if this index is less than 4, this entropy has also a gap. It will take these values, 4 cos square pi by 2k minus 1. But I don't know that if you take one of them, P index n or Q index n is greater than 4, I don't know anything. So not only P index n and Q index n is small. If you take M index P and M index Q is small also, by this previous result, that entropy, at least in the irreducible case, is well behaved with the basic construction. Using that, we can prove that if M index P and M index Q, M is the above, if this C is small, then also these possible values have gaps. And another, how much time I have?
Oh, it remains
almost done.
20 minutes. 20 minutes.
Oh, 20 minutes. So I mean, almost done. Then I'll talk about angle then at the end. Okay, so yeah, so and one small application. There's probably I should have one proof. Let me prove this one at least. I have time. So we have this P and this is Q and this one, this N, all this inclusion. And if this index is 2, whatever be Q index N, M index Q, M index P, whatever it be, and if you have this irreducibility that HP not comma, I should not say comma, this is given HP given Q is either 0 or log 2. That is the thing. So here Q index N can be small. Probably this can be generalized to super transitivity or something. I have not tried that, but let me sketch a proof of this. First, we'll use this one, that age equals to minus log lambda that I talked before. So, so to prove that age is either 0 or log 2, I'll just prove that lambda PQ is either 1 or half. So one nice thing in index for subfactor paper of Jones, he has shown that if you go through the paper, you will see that if that is the main thing he was motivated to define index. What will happen if index is 2? And the beautiful thing is that there is a Goldman type result there. I mean Goldman's result, which Jones written beautifully, that if index is 2, then Z2 acts on N. And M is nothing but N cross Z2. This is the characterization. And using this, one can show that there is always a unitary orthonormal basis for P given N. So take 1 comma unitary means U is the unitary. So suppose you choose that basis 1 comma N for P given N because it is given that P index N is 2. Now you define this operator P equals EQ plus U EQ U star. Then one can prove that PEQ will be actually lambda times EQ for some scalar lambda. So put it here, P equal EQ plus U EQ U star, multiply by by EQ. So and use that PEQ equal to lambda EQ. Then we got this. Here I should say something. Where can I write? Let me erase this and this I should mention. This is something called push down lemma. So we have this N subset M subset M1 we have, and suppose M is an element of capital M such that suppose M1 and M2 are elements of capital M, and if M1 times E1 is the Jones projection, I mean E sub N basically. So M1 E1, if it is equal to M2 E1, then we can prove that M1 equal to M2. Proof is very simple basically. You take the conditional expectation E M1 M on both sides M1 E1. So M1 will come outside because of property of conditional expectation. Then E M1 M of E1 is this is scalar Jones index. So this is M1. Similarly, if you take this conditional expectation in the right side, you will get M2. So M1 will be M2. Now come back to this proof. So using that unitary basis, 1 and U, we have defined this operator, auxiliary operator P EQ plus U EQ U star, then multiply by EQ both sides. So what we get and use this this uniqueness condition of the push down lemma M1 E1 equal to M2 E2. Then we can prove that lambda minus 1 is nothing but U EQ U star. Right? Because this lambda is same as this, as I said before. Now, this is a scalar. Lambda minus 1 is a scalar, which is equal to U EQ U star. So there are two possibilities. Either lambda is 1. And if lambda is 1, then this NPQM will be a commuting square. And if and then entropy will be 0. That can be proved easily. And then in other case, if lambda non-zero, then put U is a unitary, so you can multiply by U star. And using that, one can immediately prove that lambda will be half. Sorry. I mean, no. If lambda is 1, then NPQM will be a commuting square. And so, if it is a commuting square, somewhere I have proved that lambda PQ equals to lambda PN. Where So lambda PQ equal to Pn this inverse if it is a commuting square. Lambda P comma Q is 1 by Pn. So use that. If lambda is 1, sorry, you got the confusion. 1 second. Yeah. So if lambda equals to 1, it will be a commuting square. So lambda PQ will be 1 by Pn and P index n is 2. So lambda PQ will be half. And if lambda not equals to 1, then U is a unitary and U will be inside Q. So ultimately will be P subset Q. And remember, if P subset Q, then entropy will be automatically 0. See? In the definition of entropy to see. If HP given is 0, if and only P subset Q. So these are the two possibilities. This is just applications of whatever we have done, I just said. So what my point is that one can try this, what are the possible values of entropy, and that is what my recent research is focused on. So I'm working on this direction. So I have proved for some test cases basically. Yeah, now I will talk about some future direction. Suppose we have a pair of subfactor P and Q, then my main question is characterize this when A is equals to minus log lambda. This seems to be extremely hard. Like Popa have characterized this when this happens, minus log lambda Mn, or maybe the same as log Jones index. And this is called characterization is called extremal subfactor. So there is no notion of joint extremality. I mean, very difficult. I don't know why it is difficult, I should say. Because one of the reason is this. Suppose we have this 2-1 factor P and Q. First major problem is that P index Q need not be a 2-1 factor. That is one difficulty. So we are lying. So first you have started with the 2 subfactor theory, 2 subfactor. But that N, which is the intersection of P intersection Q, will go beyond that category. It will not be a 2-1 factor. It will be a finite, it will be a type 2-1 Von Neumann algebra. That is fine, but it is not a factor. And even if it is a factor, this can be infinite index. And infinite index, almost nothing is known basically. So one of the difficulty, as I said, is that it is not a factor. And then next one thing that index may be infinite. And another difficulty, if you assume that it is even a finite index subfactor, it's not necessarily that it is the case that n subset M, that n P intersection Q subset M, this is not necessarily irreducible. So you have to go, even if you assume that this is irreducible, that is irreducible. Still n subset M may not be irreducible. And whatever I have done in my work only works for irreducible subfactor. And beyond that, nothing is, I don't know is there anything in the literature or not. However, very recently with my colleague Satyajit Guin, it is still in the preliminary stage, and one version is on archive. So we'll very soon we'll upload version 2, where we'll have some substantial improvement, where we have described entropy beyond tried to describe the entropy, relative entropy beyond the irreducible case. So this is the name of the paper, relative position between a pair of spin model subfactor. This is a very important class of subfactor coming from commuting square and certain combinatorial data actually. So from that we can construct a pair of subfactor, and there we can go beyond irreducibility. But infinite index, so we don't know even if these two are irreducible or not. So this whole talk is extracted from this paper. This is actually published. I should update it. It is published. So this is a short note on relative entropy for a pair of intermediate subfactors. Okay, thank you.
Thank you very much, Keshab, for this very interesting talk.
Thank you.
So if someone has a question, please unmute yourself and ask. But maybe I can start by asking a question myself. So you during all your talk, you said n should be a subfactor, and at the end you consider the case where you just take P and Q, and you said it's very complicated. You should take the intersection. It's not even a factor, not even finite index, not even irreducible, etc. So my question is, can we characterize such P and Q such that the intersection is all what you want, is irreducible, finite index, factor? Can you get sufficient or necessary condition for that?
Good question. Yeah. No, but general characterization I found almost impossible, but I can characterize when the when the index is finite. And not I can correct this already done by Feng Zhu and Vaughan Jones, that this is related with certain angle operator. There is a notion of angle operator between two subfactors. So this I have not done in this lecture. So we have a notion of angle operator and also our notion of angle. So, but that is little different. This is angle operator between two subfactor by Watatani. So that is this operator spectrum is very important. So if that spectrum is finite set, then we can say that this index lambda intersection lambda p, this one, sorry, let me write. So here M, here P and Q, we don't need actually P intersection Q is a factor or not, because this is the usefulness of lambda. Lambda holds for beyond 2-1 factor also for any von Neumann algebra, whereas Jones index was defined for 2-1 factor. So this lambda M comma P intersection Q index, this is as the this will be finite. This is finite if and only certain angle operator spectrum is a finite set. That is the characterization. Best characterization is known. But this is again an abstract characterization. In practice, computations of angle operator is again very hard, because you have to characterize the spectrum, which is very difficult, right? Characterization of computation of spectrum is not always easy. But I cannot answer your question that under what condition. Actually, in Math Overflow, I asked this question once, that under what condition at least you can guarantee that P intersection Q will be a factor. So probably I don't know the answer in general, but this angle operator, by angle operator, we can say that when it is at least finite index. Okay. But again, when it will be irreducible, it's not known, because I have example when P intersection Q is irreducible and not irreducible. So characterization, it is again related to factoriality, because if you can prove that that intersection is irreducible, automatically it will be a factor, right? So this is more difficult question basically. When it will be a factor, I really don't know the answer, and probably that is what it makes this thing very interesting, because you cannot characterize. At least for some example, can you compute?
Okay. Thank you. So any other question? Yeah. Please. So maybe can you talk a little bit about what is angle? Because you said you will talk a bit about that.
Oh, I thought maybe. That because of time problem. I'll go through it. Yeah, this is some my earlier work with Zhongwei and Sion and Yunxian.
Maybe this provide just the definition or something.
Yeah, I'll try. This is probably also this is also another important invariant for two subfactor theory. My another collaborator Beth is now working with the students on these angle things. This what I will define now. So basically, if you have a group and a subgroup, if you have, people ask what is the intermediate lattice, overgroup lattice, H subset G. So set of all subgroups which are lying in between H and G. So similarly, von Neumann started this lattice theory. So given a subfactor any von Neumann algebra in subset M, let us focus on subfactor. This L of n subset M is the set of all intermediate von Neumann subalgebra, and this forms a lattice, in fact, complete lattice under two natural operations. And if n subset M is irreducible, then this lattice will be an intermediate subfactor lattice. Like this is the intermediate subgroup lattice, and And this is the exact generalization of overgroup lattice, but or this is for subgroup things, this is the generalization of overgroup lattice. So suppose we have a subfactor n cross H subset n cross G. This lattice in the subfactor sense is same as lattice in the group sense. So this is the perfect generalization. And what happens? Watatani in 1996 proved that if the subfactor is irreducible and index is finite, then this is a finite set. That is what Watatani proved in this JFA paper, following ideas of Popa and Christensen, I think. So, and then Longo in this CMP paper explicitly asked this question. In the CMP paper, actually, in both type 1 case and for the type 3 case, he has given a bound on this finite set. So Watatani proved that this set is finite. Now, Longo has given an explicit bound by index square whole power index square. And then explicitly asked this question in the CM communication math physics paper, whether this can be bounded by index power index or not. That was his question. And with Sayan Das, Zhongwei Liu, and Junxian Ren in 2018 or 19, we have proved that, in fact, it can be done better. Not just index power index, it can be bounded by 9 power index. That is what we proved. And for that, what was our approach? So here is the, again, this figure is always very useful. So we have this P, Q, and this N. Here N not necessarily P intersection Q. And if you have, and also we don't assume irreducibility. What we have done, we have found a new notion of angle between P and Q. Alpha, NM, P, comma Q. This is different from the angle operator, what Watatani did. Our approach is much simpler and cleaner, because Watatani's thing was actually angle operator as a set, angle as a set. Our thing is very, I like it is like the Jones index, basically. I'll define this thing. So basically, what important thing is that this subfactor P just can be identified with certain projection, EP. So these are called biprojection, this EP. This is by B's word. And so this is the point. So basically now subfactor become a point. VP. VP is this. So this is my Jones projection EP. Think of this as a subfactor. This is a point. And this is N, En. So this is my origin, E. So this is another subfactor, EP and EQ, now became a point. So basically, angle between these two lines in N prime intersect M1. N prime intersect M1 is a finite dimensional Von-Neumann algebra. It has a trace. So it can be given an inner product using this Markov trace. Then this is the cos inverse of this operator, EP minus En, and you make it unitize. This is the unitization. So angle between these two in the relative commuter. So this is basically, let me write here, cos alpha will be trace of EPQ index minus 1 root under P index N minus 1. So this is actually like the Jones index, because anyway, what is the Jones index? Jones index is nothing but trace of En. That is one definition, inverse of trace of En. And this is trace of EPEQ. So it is actually generalizations of Jones index, at least in, I think in this way. So this is much more natural. And one nice thing, what quite surprisingly, this actually connected with kissing number in geometry. Because we proved how we approach Longo, that we proved that angle between that P and Q, angle between minimal intermediate subfactor is always greater than 60 degrees. And that is why this kissing number came into the picture. And this is very nice, I found. And using this, we can estimate and found the bound that it is less than 9 to the power index. So, and also similarly in plane geometry, you know that there is an angle between two lines, and similarly you have an angle between two exterior angle, right? The interior angle and exterior angle. Here also you can define using basic construction exterior angle between P and Q. And this interior angle is pi by 2 is very important in subfactor theory. This is called commuting square, and its exterior angle is pi by 2 called co-commuting square. So these are very important ingredient. And I believe that this should be a nice project, but probably not very easy. What are the possible values of this angle? For that, I think new kind of theory is needed. So I finished by saying another thing, that here actually we could prove that this is n subset m. It is lattice of intermediate set, this L of n subset m. This is bounded by index power index. Zhongwei has this conjecture that I mean, he asked this question: can it be bounded? Can it have a polynomial bound? I think that is a very important question, and if you think about that, once this new theory might be developed. So this is very important. We don't know anything whether this has polynomial bound. We have only this exponential bound. So this is also another ingredient for two subfactor theory, which I have not done in this talk. So, but this is also that we have these three ingredients. One is angle between two subfactor, another one is entropy, another one is probabilistic index, and yeah. So these three, and another one probably this angle operator. So which are all related in some sense. But probably most powerful will be the Korn-Stormer relative entropy. Okay, thank you. This much I have to say about angle. I won't go to any details more.
Okay, thank you. And of course, my big question is how far this can be generalized to tensor category, as I already discussed with you. It's for me, it will be very interesting to see how much it can be.
Yeah, right.
Done.
So probably in some JLMS paper with Beth, I have done this for inclusion of simple sister algebra. So all these things can be done for type 3 also, and whatever this angle we have defined, and also more generally we can do for simple sister algebra. So
okay,
probably we should try about that tensor category also. So by the way, that type 1 and type 3 both are example of simple sister algebra. So that angle between simple sister algebra covers both type 2 and type 3. But beyond simple, even for any sister algebra, there are various difficulties in defining angle. One of the reasons is that there are not enough conditional expectation in sister algebra. So probably in tensor category, those kind of things one need to see. What are the so what do you mean by angle? There should be some subcategories, angle between subcategories.
Yeah, you consider Frobenius algebra objects. The point is how to define or generalize notion of angle between two Frobenius algebra
What are the
objects.
notions of conditional expectation there?
Oh,
that is important.
No, I don't know. In fact, it's I don't know.
That
really.
one should first think probably.
It's
But
anyway.
yeah, this is important because if you do this, then under single umbrella, everything will be there. So it is important to think probably in categorical.
Yeah. So any other question? Okay. So if not, let me thank the speaker again.
Thank you.
Thank you very much. So I hope we can see you soon. If you can join, if you can come to China, it will be very nice.
Yeah, thank you.